Last lecture we started, or finished actually, haven't started, here, the case of Fermi gas or Fermi liquid. And the main idea that is important to remember about Fermi gas is as follows. Since we have many particles in our system, we have a box of V, and the particles, the amount of particles, n, is very large. Okay. Eventually, it causes the following effect. If you look on the energetic spectrum, epsilon, even in the case when there are absolutely no interactions between the different particles, okay, so the only interaction that we have is Pauli exclusion principle, but it's extremely strong, this type of interaction. All particles are piling up one on top of each other. They will pile up to approximately mu Fermi. Okay? At approximately mu Fermi. Because of what? Remember this sigmoid function or Fermi distribution, that the occupation fraction F as a function of epsilon always looks like this. Okay? And here is mu Fermi, and it's approximately 1/2. Not approximately, it's exactly 1/2. So the only part of the energetic spectrum which is not fully occupied and not fully empty is in the vicinity of the mu Fermi. Okay. Now, how large this region is? This region is about of k Boltzmann T to the right and k Boltzmann T to the left. Okay. Why? Because we have in F is 1 over e to the power beta epsilon minus mu plus 1. This is the probability, and it converges to 1 with a rate of 1 over k Boltzmann T. So how much you have to move around mu Fermi in order to converge to 1, dictated by beta. How much you have to move upward in the energetic spectrum in order to get to 0, defined by beta. So this is k Boltzmann T to the right, k Boltzmann T to the left. Now, mu Fermi, in our specifics, what we calculated, mu Fermi for this gas was approximately k Boltzmann multiplied by 10 to the 5. Okay. Approximately. Okay. So we take a low temperature or room temperature or whatever temperature we like, as long as it's not a plasma temperature, as was mentioned. Okay. And we ask, okay, where is the region that only due to the Pauli exclusion principle, you don't even included any other interactions, where the region where some sort of dynamics can happen. What I mean by dynamics, some of the states can be occupied and then are going to be unoccupied, and some of the states were occupied and then will become unoccupied, and vice versa. It's only this region, right? It's only this region. Now mu Fermi is 10 to the 5. The temperature, if even you take the room temperature, don't go and take the extremely low temperature, right? Take the room temperature. Room temperature, the energy of the room temperature, this k Boltzmann T, is of order k Boltzmann multiplied by 10 to the 2. Okay, 200 is 10 to the 2, 3 10 to the 2, it doesn't matter. So this region where something can happen, is extremely narrow where compared to the mu Fermi. Okay? Because if you take k Boltzmann 10 to the 2 divided by mu Fermi, what you obtain as 10 to the minus 3. Okay? So 10 to the minus 3, it is the relative width of this region where something can happen. Occupied become unoccupied, unoccupied become occupied. Anything that you can affect sits over here. Now, it's not only it sits over here, in order to affect it, you have to modify somehow the mu Fermi. So basically, you have to apply extremely high interactions in order to modify something. Right? You have to apply interactions on the order of mu Fermi, because this is where this something happens, right? In order to modify something. Basically, the idea is, due to the Pauli exclusion principle, the particles pile up on top of each other, and since we have a large number of particles in our system, okay, this is why mu Fermi becomes extremely large. They pile up very, very, very high in the energetic spectrum. And then you say, well, if I want to include interactions, the interactions have to be on the order of mu Fermi in order to do something. And those are extremely, 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 extremely large interactions that you don't have. Okay? This is why this very simple picture of gaseous system is actually very convenient and very applicable. Why? Because you need extremely large interactions. Where it fails when your temperature is extremely, extremely high. When your temperature is not the room temperature, it's not 10 to the 2, it's actually 10 to the 5, 10 to the 4, right? Then the applications are starting to fail. When you have extremely large interactions, but well, you don't really have, or your mu Fermi is not so high. Okay, why the mu Fermi in our system was extremely high? It was just due to the large number of particles. Okay? They have to pile up due to the Pauli exclusion principle. And since we have a large n, mu Fermi becomes extremely large. So if you looking on a system of not a macroscopic system, but a system of few particles, this idea won't apply. Right? But as long as you have a macroscopic system with many, 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 many particles, okay, the Fermi gas perspective always works. Now you can ask me, Stas, no. You got it wrong. You got it wrong. Why you got it wrong? Well, you have particles, right? You have particles that are sitting over here. You have particles that are sitting over here. They don't have extremely large energy. All the energies that we are talking about are kinetic energy. So yes, they are particles that are extremely hot, right? They're in this vicinity of mu Fermi. Yes, they are extremely hot. You cannot affect those particles. Understand this, right? If you have extremely hot particle with extremely high velocity, it's really, really hard to modify its energy because its kinetic energy is extremely high. But I also have particles that are sitting where? That are sitting at the bottom of the spectrum. So there is zero. Okay. There are many, many particles that are around zero. They have almost zero kinetic energy. What is the problem that I will affect those particles? Only those particles. There's no problem, I will affect them. The answer is you can't. It's quantum mechanics. Right? And in quantum mechanics, you cannot pick a single particle and say, oh, I'm looking on this guy. You can't do it. The olden nature of quantum mechanics won't allow you this. Because if you somehow manage to pick a particle, right, what will happen to its velocity in the next second? To the Heisenberg uncertainty principle.
It will go to zero.
No.
Not zero, but...
Infinity, it will diverge, right? So you won't pick a single particle, and due to Pauli exclusion principle and what you develop, exactly the state will immediately be occupied by somebody else. Immediately. So quantum mechanics, the nature of quantum mechanics and quantum particles forbids you from picking up specific particles. And if you cannot pick specific particles, all those states are always protected and they are always occupied. So you cannot affect the system. Right? So it is all the nature of quantum mechanics. In classical system, it won't work. Because in classical system, it is, oh, I see this guy, it's extremely slow, it has a low kinetic energy, I will affect this, I will include interactions, and interactions will affect those slow guys. In quantum mechanics, you can't. Why you can't? Heisenberg uncertainty principle. Why it's always occupied? Because of the temperature and the statistical laws that we displayed. Why there are no several particles that are sitting at the bottom? Well, because of the Pauli exclusion principle. Okay? So this is the idea and the picture that I want you to remember about the Fermi, that particles are piling up on top of each other, and they're piling up through the roof. Okay? All right, so this is it for the fermions. We will go now to the bosons, and the bosons and Bose gas. Okay, great. Now, we will do almost everything in very similar perspective for bosons. Let's start for the simple system of 3 states, and then eventually we'll go to something which looks like Fermi gas, but always with bosons. Yes?
About the problem with picking a single particle, what happens in the case where our states are extremely sparse along the phase space, and thus we can pick a general area of the state that...
Can you pick a single particle? The problem is picking a single particle.
Not with 100% probability, but with
okay,
high
so
enough probability such that...
what will happen to the particle that you pick?
Assuming we...
What will happen according to the Heisenberg uncertainty principle?
No, we won't pick it for sure. We would pick a general area of the state.
So the area of the state is not picking a single particle. Who's sitting there?
Yes, but assuming the states are very sparse along the phase space, then even picking a general area will assure us with high probability that we pick the...
Think about it. What you're trying to do. You're trying to affect a specific particles along this line. Now you're saying, no, it's not a specific particles, are specific energies, right? Okay? You're trying to affect specific energies that will do something to this energetic space. Okay, so what will happen? Those states have to be occupied. The only thing that you will do, you will do something to your spectrum, and that's it. Still, due to this perspective over here, okay, the particles have to occupy all those states up to mu Fermi. So if you're not modifying mu Fermi, yes, you somehow modify the separation of the states over here. Is it important? No. The only thing that will happen is, well, yes, the structure of the energetic spectrum will be a little bit modified over here, okay? But still, all the dynamics is around mu Fermi. So if you modify something over here on a spectrum of around 0, it won't affect all the particles that can jump around mu Fermi.
Oh, okay.
That's it, right? So the thing is, you can affect the spectrum, not single particles. But if you're affecting the spectrum, well, you're saying, oh, this is a forbidden state. Nobody's sitting over here. I don't care because I still have a piling up particles up to mu Fermi. That's it. Okay. Other questions? All right. So let's go to the bosons. And what we know about bosons? Well, the bosons, we have that the spin is not a regular number. Oh, the other way around, the natural number. And the Pauli exclusion principle does not apply. Remember, all the Pauli exclusion principle comes from the symmetries of the Schrödinger equations. We don't really care. We only know the following, that if we have epsilon 1 and epsilon 2 and epsilon 3, okay, we can fill up epsilon 1 up to the roof. Okay. So we can put here one particle, and another particle, and a third particle, and it's not a forbidden state. Even if we put here the other two particles, it's still not a forbidden state. Right. That's the big difference. Pauli exclusion principle says one particle per given energetic state, or the state of the system, where the spin enters as a definition for the state. For bosons, you don't care, okay? But the perspective of grand canonical ensemble still holds, right? Idea, we look on different energetic states and treat them as independent entities. Okay? That's the idea. This is what we have done for the fermions. The same thing we're going to do for the bosons. Our ideas are simple. It's the application of the ideas that sometimes become difficult mathematically. All right, so what happens? Let's look on the epsilon 1 specific state. Okay, and we think that the spin is up. Okay, and we are looking on what? We're looking on the partition function of this specific state. Okay, what happens over here? So we know that we have sum up over what? Over all possible states or values that the energy have for this specific state, and the number of particles that we have for this specific energetic state. Okay, and we have to sum over all of them. So summation over all possible values of energy and number of particles. Okay, so here we have e to the power minus beta e I minus mu and I. Right? This is how we define the partition function of a specific energetic state. Now, what are the different energies and what are the different number of particles? So the energy of the state is the only thing that we know is how many particles are inside multiplied by epsilon 1, right? If there are 0 particles, the energetic contribution is 0. If there is 1 particle, the contribution is epsilon 1. If there are 2 particles, the energetic contribution is 2 epsilon 1, etc., etc. So all of this is simply a summation and goes from 0 to infinity. We don't have a limitation of the number of particles that can sit inside a given energetic state. Those are bosons of e to the power minus beta epsilon 1 n minus mu n. Right? Yep. Okay, so let's sum this up. What is this? Let's write it a little bit differently. N goes from 0. Sorry?
2 and the C.
Okay, geometric series minus beta epsilon 1 minus mu multiplied by n. Okay, so we have a specific prefactor to the power of n. So it's when n equals to 0, it's just 1 divided by 1 minus. And what is the multiplier? E to the power minus beta epsilon 1 minus mu. Not good. No. But this far away from me. Okay, so let's write it down. Z of epsilon 1 up, it is just 1 over 1 minus e to the power minus beta epsilon minus mu. Okay. What is what is?
Do the sign epsilon 1 up as an energy, like the up?
So for think about it, it's just I have spins. Spin +1 and -1.
It doesn't really matter, that's for...
Exactly. It's the degeneracy that will enter.
The energy
So,
is the same for spin up and down.
yep. So for example, if I will include a specific magnetic field, it will matter. But for us, for now, it's not.
Okay.
It's only the degeneracy that's the spin up and down for me. It's only the degeneracy of the spins per given state. So the only thing that I'm saying, okay, so epsilon 1 is the energy, but I can have bosons with +1, for example, and I have bosons with -1.
Yeah.
That's it. Yes.
A capital Ni would be the number of spin up bosons occupying energy level.
Exactly. Because the state of this energy is defined by the energy and the number of particles that are sitting there for the grand canonical ensemble. You always have, you need two parameters to define this general state in grand canonical perspective. The energy and the number of particles, because it's neither of them is constant. Other questions? Okay, so this is just for one single state. What happens to Z, the grand canonical partition function for every body? It is just Z epsilon 1 up, Z epsilon 1 down, Z epsilon 2 up, Z epsilon 2 down, Z epsilon 3 up, Z epsilon 3 down. Right? Because this marker independent. Okay. The independence means factorization in the language of partition function, or factorization in the language of probabilities. So we have these guys. Okay. Now, does it matter if I have epsilon 1 or epsilon 2 or epsilon 3?
No.
Oh, it does. It's actually yes, because I forgot here epsilon 1.
No,
So the function stays the same. Yeah, the only thing that
this is what you were asking.
the epsilon was, yes.
No, of course.
So what I have, okay, so what I have is Z equals to 1 to the power minus me minus beta, epsilon 1 minus mu to the power of 2. Right? And I have 1 to the power 1 minus e to the power minus beta, epsilon 2 minus mu to the power of 2. And I have 1 over 1 minus e to the power minus beta, epsilon 3 minus mu to the power of 2. So in general,
For each spin.
for each state, the 2 is I have only up and down. I have +1 and -1.
Yeah, that's cool.
Okay, so I can write it down in general terms as 1 minus e to the power minus beta, epsilon 1 minus mu, multiplied by 1 over 1 minus e to the beta, epsilon 2 minus mu, 1 over 1 minus e to the power minus beta, epsilon 3 minus mu, and all of this to the power of 2. And this is the degeneracy. Degeneracy. Not good, right? Degeneracy. E. Degeneracy. No, I think it's
E.
the E instead of I?
Yeah.
Okay. Okay. Great. Now, what will happen if instead of just spins +1 and -1, I would say I have 0, +1, +2, +3, -1, -2, -3. Okay? It will modify only the degeneracy over here. Okay? So the degeneracy, if we have a degeneracy per each state, enters as the power of the multiplications of different partition functions. Okay, that's it. the degeneracy will always enter in this form. Why? Again, I will just multiply each of the partition functions for each specific state with each specific value of spin. It will enter as a multiplication over here. The energy is the same, therefore it will enter just as the power inside here. Great. Now, let's look now in the fermions. In the fermions, we could say the state is occupied or unoccupied because there is also only 0 or 1. Here, the situation is different because it's not that the state can be occupied and occupied. The average number of particles can be more than 1. It can be 2 and 3 and 4 and 5 and 6 and 7, etc., etc., etc. So, fermions, the largest number of particles is 1. Okay? Bosons, a different story. So, let's compute the average number of particles for the lowest energetic level, epsilon 1, with spin up. Okay. So I want to compute N1 spin up average. Okay. How do I do that? Now, we can have the same story as we had before. We have to sum up over all the possible states of all the different representations of all the different energetic states. But we don't have to do that, right? Because we have shown that the moment that I have factorization due to independence, I can treat each state, each energetic state, independently of any other energetic state, and look only on the partition function of this specific state. And that's it. Only the partition function of this specific state. This is the only thing that matters to me. Okay, so how do I compute it? Now, there are two ways. The one is the original using the definition. It is a summation of n goes from 0 to infinity, n the probability of the energetic state epsilon 1 with spin up to have n particles. Okay? This is the expectation value. So what do we have? It is summation n goes from 0 to infinity and multiplied. What is the probability? This probability. It is the Boltzmann factor, which is e to the power minus beta epsilon 1 n minus mu n divided by z1. This guy. z1. Or z epsilon 1. Z epsilon 1.
The epsilon 1 or the epsilon 1 up there?
Does it matter?
Because you have the power.
Because of the degeneracy. Yeah, well, but okay. But it actually doesn't matter because up or down will produce exactly the same partition function. Okay. Okay, so how do I do that? Let's take this guy out. I have 1 over z epsilon 1 up. The summation n goes from 0 to infinity and e to the power minus beta epsilon 1 minus mu n.
It's the differential.
How do you call it? A trick of whom?
Ah!
Feynman trick.
Yes.
This is a Feynman trick. Okay? This is a Feynman trick. Okay. Yes, I know. So let's call all of this A. So what we have is 1 over z epsilon 1 up. Summation n goes from 0 to infinity n to the power minus a n. Okay. Now we notice that this guy is minus the differential of this guy. Mainly 1 over z epsilon 1 up. Summation n goes from 0 to infinity minus d to dA. So we did this trick in the canonical ensemble, but there was only beta, so we had to derive with respect to beta. Okay, now we don't have beta, we have something else, right? And we did it for the average energy. Here it's the average number of particles, so we have to take a derivative with respect to something else. D to the A of e to the power minus a n. We take everything out, so we have minus 1 over z epsilon 1 up summation n goes from 0 to infinity d to dA, and here we have e to the power minus a n. Okay, so what is this? This is minus, so this is minus z epsilon 1 up, but this guy, well, this is the summation of what? Of just the epsilon, so we have d to dA of z epsilon up. So we have minus d to dA log of what? Of z epsilon up. Now notice that in z epsilon up, we're writing a as beta epsilon 1 minus mu. Let's write it down. So beta epsilon 1 minus mu equals to a. Okay, so what is this guy? It is equals to minus d to dA log of what? Of 1 over 1 to the power e to the power minus a. Okay, so it is d to dA of log of 1 minus e to the power minus a, right? So it is 1 over 1 minus e to the power minus a multiplied by what? E to the power minus a. Now, we know that b epsilon 1 minus mu equals to a, right? So we obtain that n epsilon 1 with spin ups average equals to e to the power minus beta epsilon 1 minus mu divided by 1 minus e to the power minus beta epsilon 1 minus mu. Hooray, hooray, hooray. This is also has a name of Bose distribution. As the occupation probability for the fermions was named as Fermi distribution, and it had these properties of sigmoid function that led us to the mu Fermi, etc., etc. This is the expression for a single state, right, for the bosons. Now, I don't really care if it's epsilon 1 up, epsilon 2 down, epsilon 3 sideways. The energy enters over here, so this is the energy, or the average number of particles, no matter what the spin is, right? Because we have a degeneracy, and we don't have any magnetic fields that will break the degeneracy. So the general result for any value of the energetic state, it is 1 over e to the power beta epsilon 1 minus mu minus 1. Right, so the only thing that I did, I've taken this to the denominator. Okay, this is bosons. What was the result for fermions? Do you remember?
Plus one.
Plus 1. That's the only difference. The only difference, and epsilon was 1 over e, I need this, e to the power beta epsilon minus mu plus 1. Okay. So this had interesting properties about what? It had interesting properties about the mu Fermi. Okay? And the Pauli exclusion principle was applied, etc., etc., etc. What the interesting physics that we can spot in this expression? What interesting can happen?
It can approach infinity.
Exactly. Okay. And epsilon for bosons, the average number of particles for a given state, okay, e to the power beta epsilon minus mu minus 1, it diverges when mu goes to epsilon.
Or at very high temperature.
Or for very high temperatures. Now this is for any epsilon. Now, also what we know, so it can diverge. This is good. Something else that we see from this about this mu. Is it positive, negative?
It has to be negative, I think. Otherwise,
Why? Why it has to be negative?
Otherwise, the summation won't converge at all.
Okay, forget about the summation for a second. Just look on the expression. Look on the expression. So what happens if mu is approaching to epsilon, but from above?
It'll be negative.
It will be negative, right? So if mu for any you find a specific energetic state, epsilon, where mu is above epsilon, okay? So when mu is larger than epsilon, and epsilon average is smaller than 0. Okay. Right? So you see this? If this is a negative number, e to the power beta is always positive, e to the powers of some negative number, okay, e to the power of some negative number is smaller than 1. So we have a smaller than 1 number over here, minus 1. The whole thing is smaller than 1, and it can't be true. Why it can't be true? It's related to the summation, right? But why it can't be true? It's the average number of particles. Particles are 0, 1, 2, 3. There is no such thing as minus 2 particles. Okay? There are fractal dimensions. Sometimes we can say we have fractal particles, but nobody says that we have minus particles. Okay? It's not related to antimatter, not related to dark energy, nothing. It's just a limitation of what is mu for a system of bosons. That's it. Alright? So
Mu must be smaller.
mu for any epsilon of your energetic spectrum, mu have to be smaller. Specifically, mu has to be smaller than the ground state energy. Otherwise, something bad happens. The number of particles will explode, etc., etc., etc. So, the idea, simple physical idea, was as follows. For fermions, this function eventually led us to the following perspective. Particles will pile up on top of each other, and this is where they create the fermion gas, and this is why we can look on particles as non-interacting, free gas particles, although maybe that they have some interactions, but we don't care, because the only thing that what happens is near mu Fermi, it's up, up, up. This explosion over here leads us for bosons to the following question. Can we obtain, so we probably won't obtain something like this, piling up. Because this piling up happens because mu becomes extremely, extremely large. This piling up happens because mu is very, 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 very large. Okay? But here mu has to be always smaller than the ground state energy. Now, if our ground state energy is something around 0, mu is always negative. Okay. Question is, and this is what we'll show, can for bosons, so this is the energy, we obtain not a piling up of particles upwards, but no, down they can
No,
go.
down, but 0.
At 0.
Everything at 0.
Okay. Can we have something like this? And what it means and where it comes from. Because we can have a divergence of the number of particles, but the particles cannot diverge. Right? We have an experiment, and there is a given number of particles. Well, there's some fluctuations, but the number of particles cannot exceed a given number. Never. So what this actually means? Okay. What it means that the particles may be piling up, and we'll see that for bosons, instead of mu Fermi and piling up, we'll obtain something that is called Bose-Einstein condensation. And this Bose-Einstein condensation has extremely huge implications to many different specific fields like superconductivity, etc., etc., etc. So that's it for today, and tomorrow be ready for algebra Holocaust ride. We have to compute a lot of integrals, See you all tomorrow with a lot of integrals.
הבנתי בערך מה הלו"ז, לא כל כך הבנתי. צריך ללמוד להמשיך מעבד זמן זה. עכשיו יש לי דוח מעבדה במקביל להגיש. סנגד מעבדה במקביל.
כן. אתה שלחת לי את המכתב.